now that we've covered star formation, now we're going to talk about how stars evolve throughout the course of their life cycles. So we'll start with low mass stars, and then we'll talk about high mass stars. The star formation is kind of this first part of this diagram, and then today we'll focus on the main sequence and then on the old age phases of the stars, and then over the next couple of lectures we'll talk about what happens when a star dies and then what remnants are left over after a star has died. And so I think this is really where astronomy comes into its own as a science. So a lot of what we've talked about is just kind of observing things out in space, which is interesting, but the physics that's happening in these stars as they go through their life cycle is giving us access to conditions that we could never achieve on the Earth. So any experiment that you try to do, you're never going to be able to get these kinds of conditions that we're going to talk about now. So it unlocks an ability to study very exotic types of matter that we can't access on the Earth. So first we'll start with low mass stars. We'll talk about what the life stages are for low mass stars and what happens when a low mass star dies. So to review, when a low mass star is on the main sequence, it is turning hydrogen into helium in its core, and the way low mass stars do that is called the proton-proton or the PP chain. So you take these 4 hydrogen or 4 protons, fuse them together, and you get a helium atom and some energy out of it. But what happens when you don't have hydrogen left in your core and there's just a bunch of helium now? What happens? So we haven't talked about this yet, but you should be able to use some of your knowledge that you've gained to come up with a hypothesis as to what happens for the core of that star. So the fusion reactions in the core are what are providing the outward pressure that's fighting against the inward collapse of gravity. So if there's no fusion reactions of hydrogen into helium in the core, then there's no outward pressure anymore. So gravity is going to start to win, and so your core is going to start to shrink, and then as something shrinks into a smaller volume, it's going to heat up. So the core is going to shrink and heat up once there's not hydrogen to fuse into helium in the core. And so when that happens, now you're going to start to evolve off of the main sequence. So remember, the main sequence is this diagonal line through your HR diagram, and to be on that line, you have to be fusing hydrogen into helium. And for low mass stars, so the sun is what we would consider to be a low mass star. When it runs out of hydrogen in its core to fuse, it's going to evolve off of the main sequence along this path. And so what's happening now, we talked about how the core is able to regulate its own temperature. So when everything's working well, if the core gets too hot, it'll expand, cool off, have less reactions, and then stabilize itself. Or if it gets too hot, it'll cause more reactions to happen, which will cause it to expand, and then it'll cool off and regulate itself. But at this phase now, this whole time you've been converting hydrogen into helium. Helium is more dense than hydrogen, so the helium is going to settle in the center of your core. Eventually there will be so much helium in the core that it's now displaced all of your hydrogen. So you're not fusing hydrogen in the core anymore because the core is now made out of helium. Helium fusion requires a lot higher temperature than hydrogen fusion, and so now we have no fusion reactions happening in our core. So our core is helium and it's not doing fusion, so it starts to contract and heat up. Eventually, this helium core, as it shrinks and heats up, will achieve a high enough temperature that any hydrogen that's kind of touching or near the core, this helium core, will be hot enough that it starts doing fusion reactions. But this is not a stable process because the core is still not doing nuclear reactions, it's still shrinking and heating up. The star is going to puff out in size, so you can see the size difference between your main sequence star and now your giant star. And that's because the temperature needed to do helium reactions is much, much higher than to do hydrogen fusion reactions. But as this core is shrinking and heating up, it actually does achieve a temperature higher than normal hydrogen fusion reactions. So this core the shell of material that's doing hydrogen fusion around this helium core is actually at a higher temperature than the core of the main sequence star that was doing hydrogen fusion. So this shell is at a higher temperature, and so it's actually putting out more energy than the hydrogen core fusion reactions were. And so there's more energy now spreading throughout the whole star, and so the star is going to expand to try to cool off to dissipate that extra energy. And so that's why the star puffs out when it reaches this stage where there's a hydrogen fusing shell but an inert helium core. Eventually, if your star is massive enough, the core can achieve a temperature high enough to convert helium into carbon. So this is the helium fusion reaction. It doesn't work with just 2 helium, so you need to do a complicated reaction that has 3 heliums as its input, and you get a carbon-12 nucleus out as the output, and then a bunch of energy in the form of gamma rays and neutrinos. And part of the reason you need such a high temperature is these helium nuclei have a positive 2 charge, so it has double the charge of a hydrogen nucleus, and so you need a lot higher temperature to overcome the repulsive force of all these positive charges. But if your star is massive enough, it will overcome that and start to do helium fusion in its core. So this is when the helium fusion starts, is called the helium flash, and now you're doing nuclear reactions in your core again, so your thermostat is going to be back in equilibrium. And so obviously when you start doing nuclear reactions, you're going to start outputting a lot of energy, and the core's temperature is going to rise, and eventually it will reach a steady state where it's now doing these helium reactions in the core and stabilize. And once your star is stabilized, now you've got this helium core that's doing nuclear reactions, and you still have this shell of hydrogen around that core, that helium core, also doing reactions. And so your equilibrium is restored for the time being. And your star will actually shrink not all the way down to its normal main sequence size, but to a smaller size than its red giant stage. So main sequence, you're just turning hydrogen into helium in the core. Then once there's enough helium in your core to displace the hydrogen, you're evolving off the main sequence, and you're starting to fuse hydrogen in a shell around the helium core that's not yet hot enough to do nuclear reactions. Then you're a red giant. Once the core starts doing helium reactions, then you kind of settle back down into a more stable state as a subgiant, and that's as far as we've gotten so far. And so when we look out into space, we see stars at these various stages. So we've got our main sequence stars, we've got our subgiants and red giants, and then we've got this horizontal branch where we're doing helium fusion reactions in our cores. And so what happens when a low mass star reaches the end of its life cycle? So again, we'll cover this in a moment, but let's see what kind of hypothesis or theory you can come up with. Yeah, so it'll be a similar process that we saw before. So this helium fusion was turning helium into carbon. So eventually your carbon is going to displace the helium, the helium in your core. And so you can get the shell of helium to start fusing around that inert carbon core. This phase is called double shell fusion. So you've got a core that's made out of carbon that's not doing nuclear reactions. Then outside of that, you have a shell of helium that's fusing. And then outside of that, you have a shell of hydrogen that's doing fusion reactions. So this is double shell fusion, and this is never going to be an equilibrium state. For example, if the helium shell starts putting out more energy, that'll heat up the hydrogen shell, and there's no way for them to ever, one to cool off and the other one to compensate. So eventually there's the series of pulses that just go throughout the star, and eventually one of these pulses will be so violent that it just rips the star apart. And so that's the result of that is called a planetary nebula. So all of this material here is all the outer layers of the star that have been blown away from one of these thermal pulses. And at the center of this nebula is going to be a white dwarf. And that white dwarf is the core of that star. And because that core was all the carbon that was not doing fusion reactions, a white dwarf is made out of a special type of carbon. And so here's another picture of what a planetary nebula might look like. So in a low mass star, you get to the point where you've fused helium into carbon, but then you're never going to do carbon nuclear reactions. You can get some helium fusing with carbon to make oxygen, but you're not going to get a full carbon fusing with another carbon to make a heavier element. And you might be wondering, why doesn't this core just keep collapsing? And so we talked about degeneracy pressure when we talked about star formation. And so in an atom, there are quantum mechanical effects that are preventing you from collapsing into a denser state. And so the carbon in the white dwarf is being supported by this degeneracy pressure. So it's not like normal carbon that you would find in your pencil lead or something like that. This is a very exotic form of carbon that's being supported by this quantum mechanical effect. So the full cycle, main sequence, the helium displaces the hydrogen. The hydrogen will eventually start fusing in a shell around the helium. Then the helium fusion reactions will start, and now you've got a more stable situation where you have helium fusion and hydrogen fusion. Then the helium fusion is producing carbon. That carbon will displace the helium. You'll get back to a red giant stage. And then once you have helium burning and hydrogen burning in shells, it's not stable, and the star will eventually blow itself apart. And once it's blown itself apart, the core is all that's left, and that's what is left over as a white dwarf. And so this is how the sun will evolve when it reaches the end of its life cycle. But we've still got billions of years to worry about that. So if you shrink kind of the history of this star into a year, then for the first few months you're gathering all of your dust and making your dust cloud out in interstellar space. Then in March, you'll get a protostar, and from March to the end of November, basically, you'll have a normal main sequence star. Then from November to almost the end of December, you'll have your red giant stage. Then for a couple days at the end of December, you'll get your helium core fusion starting, and that'll be more stable. And then for a day, you'll get the double shell fusion happening, and that's very unstable, so it doesn't last very long, and you blow yourself out, all the material out in a planetary nebula, and all that's left is a white dwarf that will last for a very long time until it interacts with something else. And that's something we'll talk about over the next couple of lectures. So hydrogen fusion core for main sequence, then hydrogen fusion in a shell around a helium core for the red giant stage. Helium fusion will eventually start and you become more stable. And then this helium will be displaced by carbon. Helium and hydrogen shell fusion is unstable and it'll blow itself apart, leaving behind a planetary nebula and a white dwarf. So for high mass stars, we'll do the same kind of thing. What are the life stages for a high mass star? We'll start to talk about some interesting consequences of these stars doing these fusion reactions, and then we'll talk about what happens when one of these high mass stars die. So the low mass stars do a proton-proton chain nuclear reaction, but the high mass stars have access to a different way to do fusion reactions. So this will only work if you have carbon, nitrogen, and oxygen already in your star. But if you have those elements, then so the total reaction is still your 4 hydrogen or 4 protons fusing to make helium and getting a bunch of gamma rays out and positrons and neutrinos. But instead of doing it proton-proton chain way, we have the CNO cycle. So you'll basically use carbon, nitrogen, and oxygen as catalysts to do a slightly different nuclear reaction. So our first step, we're going to take a hydrogen nucleus and a carbon nucleus and fuse them together. We get a gamma ray out, and that fusion results in a nitrogen nucleus. So nitrogen is just just adding a proton makes it become a nitrogen. That nitrogen 13 is not stable, so it's going to decay and give off a neutrino and a positron. And now that decay results in carbon 13. That carbon 13 fuses with a hydrogen, and you get a gamma ray out, and nitrogen 14. That nitrogen 14 fuses with hydrogen, you get a gamma ray out, and oxygen 15. Oxygen 15 is not stable, so it decays into a positron and a neutrino, and then that leaves you with a nitrogen 15. That fuses with hydrogen, and you get out a helium 4 and a carbon 12. And that carbon 12 can go back into starting the next cycle for the CNO cycle. So you can only do this if you have a high enough temperature. So carbon, now you've got even more positive charge in your nucleus, so you need a really high temperature to overcome that electromagnetic repulsion. And so that's why the low mass stars don't have access to this cycle, but the high mass stars do. Higher temperature allows you to overcome the electric repulsion. So I don't necessarily expect you to know all of these individual steps, but you need to know that high mass stars have the CNO cycle and the low mass stars do the proton-proton chain. So the stages for the star after it leaves the main sequence will be similar to the low mass star. So for being on the main sequence, you're just doing hydrogen fusion in your core. That's just CNO cycle instead of proton-proton chain. Then you become a supergiant when you have your helium displaces your hydrogen in the core, and you get a shell of hydrogen burning around that helium core, and then that helium core will eventually heat up enough to do its own helium fusion reactions. So those first stages are similar to what we saw for the low mass stars. But then, because the high mass stars have much higher temperatures, there's a lot of extra stuff that they can start to do. So we'll start to see things like helium, carbon, oxygen, and neon fusing to make even heavier elements. So we can start making oxygen, neon, magnesium. And so part of what we're going to talk about now is how do we build all of the elements in the periodic table using stuff from space. So all of these elements are going to have to be created by the universe in some way, and inside of the cores of stars is the way that we fill up basically the first half or the third of the periodic table. So we'll come back to talking about the Big Bang at the end of the semester, but after the Big Bang, all that you have is hydrogen, helium, and a little bit of lithium. So 75% of the universe is hydrogen, and 25% is helium. So everything else has to be made by stars, basically. In a low mass star, you confuse your hydrogen into helium, and then your helium into carbon. So now we're getting a bit more of the periodic table filled in. The high mass stars are using the CNO cycle, so they're building up carbon, nitrogen, and oxygen. And then this process of the helium fusing with these various elements is called helium capture. And so we're building up oxygen, neon, and magnesium. And when we look out into space, so this graph is the chemical abundances of the elements in the periodic table as seen out in space. So there's tons of hydrogen and helium from the Big Bang. There's not a lot of these elements that are not a result of fusion reactions. And then we see there's a big spike for carbon, nitrogen, oxygen, because those are part of the CNO cycle. Then there's another dip. Then neon has another spike because of helium capture, and so does magnesium. And then we'll see why silicon, sulfur, and iron have spikes in a moment. And towards the end of the lecture, I'll show you a cool periodic table where we talk about where all the elements come from. But for what we're talking about now, basically all of the peaks are from fusion reactions or helium capture in the cores of these stars. So past the helium capture, if the star has enough mass, so these are stars that have more than 8 solar masses, now we can start fusing heavier and heavier elements in our cores. So we can fuse carbon and oxygen together to get silicon, or we can do 2 oxygens together to get sulfur. So that's why the silicon and sulfur spikes were in that graph. And then you can fuse 2 silicon together to make iron. And just a note, the silicon reactions don't go straight to iron. They go to nickel first, and then the nickel decays into cobalt and then iron. So now we've built up our periodic table to include silicon, sulfur, calcium, and iron. And as this is happening, there are several different fusion reactions going on all at the same time. So you get these different shells. We've got still our hydrogen burning shell, then helium burning, carbon burning, silicon burning, neon, magnesium burning, and then you'll get down to a core of iron. And the physics will change when we get to iron. And so this is just the material around the core. The star is still made out of mostly hydrogen that is just a gas. It's not hot enough to do fusion reactions or anything yet. And so we have these nested shells of fusion reactions all happening.
For your information, there's a lot more to ogres than people think.
Example?
Example? Okay, ogres are like onions.
They stink?
Yes. No.
Oh, they make you cry?
No.
Oh, you leave them out in the sun, they get all brown, start sprouting little white hairs.
No. Layers. Onions have layers. Ogres have layers. Onions have layers? You get it. We both have layers.
Oh, you both have layers. Oh. You know, not everybody like onions. Cake! Everybody loves cakes.
So, onions have layers, ogres have layers, and so do these massive stars. So, what happens when we get to iron? So, it turns out for all of the elements that are lighter than iron on the periodic table, if you do a fusion reaction with those elements, you get more energy out than you put into the reaction. On the other side, for things heavier than iron, if you do a fission reaction, so if you split that atom apart, you get more energy out than you put in. Iron is kind of the valley of these two sides. So iron is the most stable nucleus, and so if you tried to do a fusion reaction with iron, you would get less energy out of the reaction than you put into it. Or if you tried to split it apart, you would get less energy out than you put in. So this is basically a dead end for your fusion reactions in your core. Remember, all of these other fusion reactions were generating massive amounts of energy to help support the star from this crushing weight of all of its gravity. So if you no longer are generating any energy with your fusion reactions, and you might even be losing it, then something very bad is going to happen to your star. So how does a high mass star die? And one of the ways that they can die is in a supernova explosion. So your iron is going to start building up in the core, and you'll get to a point where, so we talked about degeneracy pressure holding up your white dwarf. Eventually that's not going to work for the iron in the core. And so the core is going to suddenly collapse and create a supernova explosion. And the reason your degeneracy is no longer going to apply is because you can get to a point where the pressure is so great in the core that protons and electrons will start to fuse together and create neutrons. So that reaction, the charges there's one positive and one negative, so that's a neutral charge. So you get a neutron out and a neutrino out. So at the center of your core, now you just have a buildup of neutrons. And so depending on the mass that you have in your star, what's left over might be what we call a neutron star, so the core of a star made completely out of neutrons, or if there's enough mass, everything might collapse into a black hole. And we'll have a whole lecture on black holes next week. So if iron is the kind of the dead end of fusion reactions, how do we get all of these other elements? So when your star goes supernova, it basically is going to release tons of energy all at once. And that energy is enough that you can start fusing these heavier elements and filling out the higher end of the periodic table. So you can get elements like gold and uranium as a result of these supernova explosions. And so that process is called the R process, and basically what's happening is a bunch of so let's say you had a bunch of these heavy elements. They can capture things like protons and neutrons flying off from the supernova explosion, and if they catch enough of them, they can build up into these heavier and heavier elements. And so here's kind of a joke, but kind of serious for astronomers. So for astronomy, we consider everything that's made in stars to be metals. So that would mean the only things that are not metals are hydrogen and helium, because those were made during the Big Bang. And then everything else is a metal. The perhaps more scientifically interesting periodic table looks something like this. So the different colors are describe how these elements are formed. So hydrogen is all from the Big Bang, helium is mostly from the Big Bang, and then some of it is built up in low mass star nuclear reactions. This red kind of fills in the gaps where the fusion reactions aren't really going to produce these. But so cosmic rays are just particles that are kind of flying through space, and so you could imagine a heavier element like carbon or nitrogen might get hit with a cosmic ray and split it into these lower mass elements like boron and beryllium. So that's what the red squares are. All of the yellow are things that are made in high mass stars or as the result of high mass stars going supernova. So that's how we're getting these things beyond iron. We'll talk about merging neutron stars and exploding white dwarfs next time, but those are basically the remnants of dead stars, and if they happen to interact with something else, then you can build up these heavier elements. And some of these elements in gray are stuff that we either don't find naturally out in space, or we haven't come up with a way to make them yet using astronomy. So there are some things that we just make in the lab because we set up very specific conditions to bombard heavy elements with protons, and the results only last for a very short amount of time. But for the most part, we can build up the whole periodic table with the reactions happening in stars and dying stars blowing themselves apart. What's left when a star, a massive star, blows itself apart is a supernova remnant. And so this is the Crab Nebula. And so if you remember way back in the beginning of the semester when we talked about what ancient astronomers saw, there were ancient Chinese astronomers who saw a new star in the sky. And we have figured out that the new star they saw in the sky was this supernova, and now we can study its remnant with our telescopes 1,000 years later. Inside of the Crab Nebula is a pulsar, which is a fast rotating neutron star, and there's a lot of cool science we can do with that, and we'll talk about neutron stars next class. There's also been much more recent supernovas than that. So the closest supernova in the last few centuries was 1987A, so about 40 years ago now. And so this picture of the sky is what it looked like before the supernova exploded. And then after the supernova, you can see this very bright new object appear in the sky. And this was a very important event for astronomy because this was the first time we detected neutrinos from something other than the sun. So this supernova happened in our galaxy, and we could observe obviously the light from it, but also neutrinos that were generated in that supernova explosion. So if we shrink the life cycle of a massive star using the same scale that we did for the low mass stars, now we don't even make it through a day. We just make it a few hours. So the high mass stars live very short lives compared to the low mass stars. So if we start at about midnight, we can form our star in a minute. Then we're on the main sequence as a blue star using the CNO cycle to make helium in the core. Then the helium displaces the hydrogen and we become a supergiant. Then helium starts in the core, so we kind of stabilize a little bit. But then the helium in the core is displaced by carbon and then exceedingly heavier elements, so we become unstable again. And once we get to iron fusion in the core, then we blow ourselves apart in a supernova explosion, and we might be left with a neutron star or a black hole after that explosion. And this all happens from 12 a.m. to not even making it to 4 a.m. So the low mass star made it about a calendar year, and on the same time scale, a high mass star doesn't even make it past 4 a.m. in a single day. So very different time scales for how quickly these things evolve. So the mass of the star is what determines basically everything about it that will happen in its life. So high mass stars live very short lives, and they can make iron in their cores, and if they get to making iron, then they will blow themselves up in a supernova explosion. The low mass stars live much longer, and they never become hot enough to make it past carbon fusion, and they'll be left with a carbon nucleus in the core of their star, and when they blow themselves apart, what'll be left is a white dwarf. And so the summary of the low mass star: hydrogen and helium in the core on the main sequence. Then you become a red giant when you have hydrogen around a helium core. The helium core will start to do fusion. Then that helium will be displaced by the carbon, and you can get double shell fusion, which is unstable, and the low mass star blows itself apart, leaving behind a planetary nebula and a white dwarf. High mass stars, similar. Helium or hydrogen into helium in the core. Then when you have helium in the core, you'll become a red supergiant, and hydrogen will fuse in a shell around that helium core. Eventually the helium will start to fuse into carbon, and this is where they diverge, in that the high mass stars can start doing carbon fusion reactions and even higher element fusion past that, and eventually they get to iron that's not going to release energy, and so they blow themselves apart in a supernova. And what's left behind will either be a neutron star or a black hole.